talk today about optimization methods in Python, and more so about modernization of some of the optimization methods. And by that I mean, well, optimization theory there's been new algorithms over the course of the years, things like random forest, are fairly recent, and a stochastic optimization technique that's seen a lot of growth in the probabilistic community, but optimization itself hasn't changed too much in how it works since essentially the 60s. And what I mean by that is there's been certain evolutions of classes of optimizers that have happened over the course of the years, gone from steepest descent, basically steepest descent, gradient descent based optimizers, to things that are genetic algorithms that use randomness to hop between basins. That was as computational power started to get a bit bigger, and we actually had real computers we could run on and leverage parallel computing and longer run times. We were able to do things like differential evolution, and so that was a change in optimization, but they still basically run the same way in that optimization is a blocking process. It's essentially when you run an optimizer, you pass it a function, and that function is called over and over and over and over and over again in a loop until some termination condition is met, and then you can move on. And that loop is inherently serial, right? Because it's time iterative. The way optimization algorithms have been built, and this is part of what I mean, modernization, the way that they've been built is they, for the most part, depend on the history of what's gone on before, which makes sense if you're trying to navigate a surface. So if you're driving downhill and you want to go downhill, you should have a record of where you've been to know which way downhill is, and that's how most optimization algorithms have been built. Even the ones that jump around a little bit, they still rely on history. However, so I will, I'm going to start this basically with an introduction to optimization itself, and then a lot of the current methods and the different variances between them, and what they're used for. The use is basically to get you, I think, to a place where you have a good handle on the Python tools, the standard Python tools for optimization, and then talk about a new shift, basically, in optimization theory to leverage the rampant parallel computing that's around, basically, these days, and that's contained within the Mystic package. So I will talk about that after we go through the introduction. Do we have any install issues that people are screaming to? Yeah. It's Python 2, yes. No, so I think in Pathos should probably be Python 3 within a month. I'm basically almost done converting it to 3. It may take an afternoon. I just haven't had the afternoon. I forked parallel Python and converted that fork to 3, and I forked the multiprocessing. So the fork of the multiprocessing is now fully compatible with the new versions. The SSH code in there is up to par too as far as Windows, and should be 2.3 compatible. I just basically haven't run 2.3 on it and finished a job off and cut a release. So it's no hope right now, but yeah, I think next month that'd be a different answer. So everything, hopefully we got, it should be easy installs. Yeah.
I'm seeing a slight, if you check-in reports of what's actually there, the stuff seems to be there. Just trust that it's going to work.
Okay, if there's something that's different,
Figure it out some other time.
sounds good. Yeah, I don't know, maybe the check-in scripts suck. I think I had a problem with mine in the class before too. I think it was spewing some extra stuff. All right, so basically, for optimization, we have basic components, and the basic components to optimization are our objective function, also called the cost function. I will probably call it the cost function more often than I'll call it the objective function. They're the same thing. It is the target of the optimization. It's the thing you want to run the optimization upon. And the other part of the cycle is the optimizer itself. So essentially what we have is something like this. Here's SciPy optimize, where we have fmin, which is function minimization. It's Nelder-Mead simplex, I believe, which is a type of optimization algorithm. And what you do is you pass the function to it. You pass the objective to the optimization algorithm, or in this case, the optimizer. And for the simplex cases, for a lot of the steepest descent algorithms, you have to pass it an initial value. So we're passing a place to start at and the function. And what that is that's the initial x value. So it would be evaluated as objective at 3, at vector 3. And that would give you your first y value. And then the optimizer essentially finds what that y value is, uses the algorithm in the simplex. What it actually does is it takes the main point, and then it has usually 4 points around it that it calculates. And those 4 points serve as anchors on the landscape. And it basically says, this one's lower, I'm going to move over here. And then it does it again, and it finds the lower one. And it keeps doing that, and it basically spider walks or crab walks down the landscape, so the steepest descent. You can think of all optimization functions as up blocking till done. Basically, whatever the termination conditions are that are built in, when they're satisfied, then you get your result back. And in many cases, you don't know what goes on before then. You just wait and listen to your fan burn. Here's a very simple objective function. It's just a Python function. It's actually poly1D here, one-dimensional Python function. And the typical optimizer will take a vector basically you have one argument. The optimizer takes a function that takes one argument where it's a vector. A vector here in the case, one-dimensional vectors. That's why we have 3 at length 1. So if we were to have more, if there were other parameters here instead of a 1D polynomial, we would have a longer list here that would be passed as our initial guess. And here we get our result out. This is the solved value. This is our optimum. And we print the optimum. You can see from the report that the current function value, which means the objective evaluated at the solved value, gives us minus 2.47, et cetera. It took 20 iterations and 40 function evaluations, a little mini report that all the SciPy optimizers produce. And then it tells you your value of x, because I printed it out. So steepest descent, yeah. Yep. So it's one of the faster algorithms and one of the least robust. If we look at matplotlib over here, I can now plot my function. So here's our polynomial, and it's the objective at x. Here is now a plot of the solution point and the objective at x. And I could have, if I'd had the value returned from the optimizer, which I didn't, if I had the y value returned from the optimizer, I could have just used it, but I didn't have that returned. It just returns an x.
It never returns the y value?
You can make it return the y value. I just didn't the first one. So I had to actually calculate again. And you can see by eyeball, that looks pretty much like the minimum. So that's a fairly typical optimization and a somewhat fairly typical validation that we got good results. The eyeball norm is the #1 way that people check things are right. That should tell you that there's optimization is a black art in some senses. The way and that's mostly due to the software construction, which hopefully will change that. There's some other things besides the basics of the cost function and the optimizer itself. There's box constraints. So box constraints are very useful in that, let's say, what you wanted to do is bound some of the dimensions a little bit. So here's an optimization on a Bessel function, so first order Bessel function. And we're going to be working over from 2 to 7 on this first order Bessel function. And here I'm going to use the more up-to-date, I was using the older SciPy interface for the first one, which only returns the x value. If you use the more modern SciPy optimized interface, what it does is there's a little bit of an abstraction around the optimization algorithms. You don't actually have to know the name of the particular algorithm you want to run anymore. What they decided was, so optimization is funny in that because the way a lot of optimization algorithms are built, they don't all behave the same. So a lot of them are targeted for specific cases. Like there's the Coblia algorithm, which is targeted for linear approximation, where you're fitting data, essentially. Least squared is also a fitting data type of algorithm. So they all have target use cases in mind, and a lot of the algorithm is customized to that particular type of case. And some of them might take bounds because of that, and some of them might have a particular termination condition that tells you when you're done because of the particular intent they have in mind. And what SciPy package has done is essentially said, well, you can configure your optimizer to use a particular method by asking, I believe, for strategy or give the method name. But you don't have to. You don't have to know it, and it'll choose the best or robust sequence for you. In this case, it's using fmin bounded. That's fmin bounded, which is a bounded Nethermede simplex algorithm, which allows you to set constraints, range constraints. So a lot of these optimizers don't have the same interface, and basically they don't have the same API. They don't require a lot of the same things, and SciPy optimizers has helped in making a more uniform API. So this still, just like any optimizer will do, it takes a function, there's the Bessel function, and then takes some arguments. And in most cases, if you're using a bounded minimizer, you don't provide an initial condition. However, if you're not using a bounded minimizer, you tend to provide an initial condition. So that's just a rule of thumb. In this case, it's bounded fmin. There's no initial point we start from, but we're bounding the solution between 2 and 4. So it's going to randomly pick some point between 2 and 4 as the start, and then try to find downhill, basically. Okay, and then we get a result back. We don't get the solved x value back. What we actually get is a result object. So a result object is, instead of just having a value returned, we get a class instance, basically, where the class instance has a lot of things to it. Result.x is the same as we got in the older days. Result.x gives us the solved value, but we can also get result.func, which is the y value, which is the y value at the solved point. There's also the number of function evaluations, NFEV, number of function evaluations. All sort of cryptic 3 and 4 letter things are returned on a result object, number of gradient, and number of ndev, I believe, is the number of gradient evaluations. There's Hessian evaluations, et cetera, that you can see on the result object that give you a little bit more of analysis. Sometimes they'll be empty if your optimizer doesn't use that type of construct. So if it's not a gradient optimizer, you'll get none for that. But here we get our result back, and in this case, instead of, I think, stupidly, instead of just taking the result function, it's evaluating the function one more time, which, well, it's my code to show as an example, but instead of doing that, I could have just shown you result func instead of evaluating it again. And what you get out of that is here. it's found the lowest point on the curve, seen by the red dot, between 2 and 4. Right, it's bounded between 2 and 4. So,
So by the way, that J1, I think should be SS.J1, because otherwise, that's not what it's on.
is that not, oh, yeah, yeah, yeah. There we go. Somehow I missed that. Yeah. I don't know how I got the plot. I must have changed the code somewhere along the way. All right, IPython notebook, a fun thing. All right. That's right. Okay, thanks for the bug report. Now, so we have these different types of optimizers. So here's the case of some things that we might have. Like I said, we might have box constraints. So there was a box constraint. We can constrain the dimensions essentially by saying we have a box, and any of the variables are stuck within that box. There are no kind of most optimizers, and what I mean by most optimizers is almost all optimizers except for Mystic really don't give you the ability to add a functional constraint where we can say some envelope in space is where we want to operate. So you're stuck at saying some box within space we want to operate out of. That's how it's typically set up, is you have box constraints on some optimizers, not on all of them. And some take gradient or Hessian information. So here, if we look at Mystic contains a lot of test functions, nonlinear test functions in the models subpackage. And all of the models come with documentation about what the function looks like and where its known minima are. And also it gives you a nice, there's a model plotter within Mystic that if you basically use the configuration that it says, hey, look at it with this, it shows you a nice picture showing the critical features of the point. It is it's got a good help line, command line help for it, but otherwise it's nice and cryptic as any other good shell command-driven tool is, right, where it takes several options. So this basically says set the box to -3 to 3 with a scale of 0.1 and -1 to 5 with a scale of 0.1. And since it's a 2D plot, the third dimension plot at 1. Okay, and here D is make a 3D plot instead of a 2D plot. So that's a 3D contour surface, and this is magnification. So I am going to right. Yeah. So what do I have to do? Okay. So that basically says that it's not finding my path. I need to.
That's the only command that you want to.
Right, but it's a shell script. Right, so the deal is, I have to, let me make one of these new files. And say Python, right? And it comes up 272, right? So that means I need to do user env. Or whatever I called it. Okay. Oh. Interrupt the kernel. Fun. No. It's basically Mac ports. Yeah, it's because I have all sort of different Pythons installed, and I just have to import the the last tutorial. My laptop totally crashed, right, and I basically lost the path information out of IPython, so I just have to. I have a script that I just have to inject here. It'll just take a second. User env, gotcha. All right. Oh, I think I do it like this. Okay. Okay, that's what I can do.
One thing is, it seems your check script
No, no, no.
doesn't check for CVX.
What's that?
I was just saying the check script doesn't check for CVX.
It should, but it should. That's just what I was about to do, yep, yep. Load, actually. I was going to do a load, and that should do it. Just by executing that guy, right? Oh, don't do that. All right. Didn't work. Restart. It's not a huge issue, but wait. Maybe it's already doing what it should. Yeah, that's fine. It's fine. Okay. All right. Okay, so let's see if we get this to go again. No.
What are you supposed to see when you run that line?
It plots, it shows a plot.
I don't get anything, which I think because
It's not inline, it's a shell command, so it
it's
should,
not. Right, but the mystic model plotter, I can't find it in my path, I don't think it's in the repository.
it should, if you installed Mystic, it should be on your path. So, Mystic model plotter. So that's this is I see. So the Python 2.7. Okay, there you go. It was because my computer hard rebooted, basically. Oh, that's crazy. All right, so I just basically restart IPython is what I have to do now, and then I'm good. Okay. Okay. Python 2.7. Okay. Right, so you should be able to type it and it should say index out of range if, because we're not passing it anything.
If you run on the command line,
If you run it on this, just the name,
like the full command with all the arguments.
Model,
Okay, so yeah, I don't see that at all. I should see it.
behind it, it's behind the browser.
In another browser window?
No, it's run from the shell, so it's not going to show up in line.
Right. I don't see any other windows, so, and if I run it in the shell, I don't see anything. Same here. So I don't see anything showing up, I have to use the browser.
Yep.
I mean, should. I don't have an icon down here, but if I look at the browser, it should be anything.
Okay. And because of the,
It has run end-to-end.
hmm?
It has run end-to-end, the whole notebook. The whole notebook as is has now run end-to-end. So it's at least runnable in principle. Right?
should work just fine. Like I said, it's should work just fine. I don't even, let's see, where is my, okay. IPython notebook. Oh no. There we go. I have another active IPython notebook up somewhere probably. I just the magnification on the screen is so big. All right, that's why we love these things. So let's see. Here we go. Okay, that goes, which is good. Matplotlib inline. There's the plot. There's that plot. It worked. There's Mystic. That worked. So this is good. And there's that. That worked. Right? So, see, it was just from not having the path configuration there. So here's what the Mystic model plotter shows. It's basically what your function looks like. So for any of these guys, this is a nice test surface because it's a fairly easy function, but there are a couple minima. There's a minima there, there's a minima there, and that's the global minima. So Mystic model plotter basically does a surface plot for you, and it is so you don't have to know how to do these things. Basically, there's the 2D plot of the same picture. Okay. All right. So that's the guy we're dealing with for Rosenbrock. And Rosenbrock is basically looks the same in 3 dimensions and above. For 2 dimensions, it's a little different, but for 3 dimensions and above, it looks basically the same. 2 dimensions, here, we'll look at the 2-dimensional case. 2 dimensions, it looks kind of like this, where it's even more complex, right? Again, we're optimizing by eye, and we could see that the minima is somewhere around here, somewhere around these points over here somewhere. It turns out that your eye is much better than most optimizers are in low-dimensional cases. So all right, so here's again, SciPy optimize, and we're going to do a 5-dimensional Rosenbrock. So here's the Rosenbrock function. It's a pretty standard test function, so even SciPy optimize has it too. We're doing it that initial guess, and then we get the results object. Here it'll give us our value where we found the minima, and the Rosenbach is basically 1, 1, 1. So it found 1, 1, 1, 1, 1 everywhere pretty closely. We can get the number of function evaluations. It took 581 function evaluations to find. And here now, if we decide to use the optimize again on the Rosenbach function, but we're providing the Jacobian, which is basically we need the derivative of the Rosenbach function. If we just happen to have that laying around, then you can use it, and it'll actually, because you've provided Jacobian, SciPy Optimize will select a better algorithm for you. It'll select one that can utilize the gradient information. So now, instead of doing something with the steepest descent, we're going to do gradient descent, and this is actually, I believe it should use probably Pal's gradient, Pal's derivative optimizer, but it could use BFGS. Either one are both good. Now we can get the result again and check the number of function evaluations and the number of derivative evaluations, and we can see that it finds a much nicer, tighter one than previous. And it took far less function evaluations, although it did take a number of gradient evaluations as well, but still faster. And the thing that you should note is, even though we found ones which are the right solution, here is another standard check you should do for any optimizer, is you've got the result once, how do you know you got the right answer, right? So if it was cheap, like this function evaluation was, and you don't know what the answer was, this is also a very good check. Eyeball norm on a graph, which is why you should have a plot of all cheap objects where you could look at it and decide. That's why I said black magic, right? This stuff is like quantum chemistry, essentially, which is optimization, right? Which is there's demons in there, and you basically hope things turn out right. And here, so we run this optimization just 5 times with a random initial starting point between -20 and 20. And you see that we get 1, 1, 1, 3 of the 5 times. And then we don't get 1, 1, 1 twice. So it looks like those points are pretty much the same. I bet that's the other hole. I bet that's the other hole. When I plotted it, there was those 2 deep holes. I bet that's the other hole. We've been very successful at finding both holes. If your goal was to find the global minimum, you found it almost 50% of the time, a little bit more than 50% of the time, right? If you only ran this the first time and this is what you got, if you ran this once and this is what you got, oops. Right? And that's how most optimizers are. They're hard, don't trust them.
So if you have a problem, which I imagine a lot of them, where you don't have the benefit of knowing the answer, how are you supposed to determine when you succeeded or not?
So in general, blind faith. And after that, scientific investigation, right? So this is a very good analogy. Optimizers are the laboratory of mathematicians and theoretical scientists, right? So if you're a physicist, a chemist, or whatever, You may have a laser lab or something like that. You put a sample in the laser or in some instrument, and you basically have to run tests on it. You get a result, right? But does this result mean anything? Now you got to run another experiment to verify that you got your right answer, right? An optimizer should be treated the same way. It's a theoretical scientific instrument with a lot of knobs. Most good optimizers, and Mystic has tons and tons of knobs. You need to be able to turn the knobs, tweak the knobs, check what happens, come up with a scientific process for how are you going to verify that the result that you got is good. And that's part of the process that, so 20 years ago, people would run an optimizer. It was expensive, there wasn't a lot of computing power, and they'd publish a paper. 5 years ago, you'd still get the same kind of thing still happening. There's been a push for code validation and data science validation in papers and reproducibility, and that's killed a lot of the people basically just running an optimizer and popping out a result, but it still happens. I mean, you most of the time will not get the same answer. You have to undergo a scientific process to analyze your results.
Is like doing a course grid search over your coefficient space, making a map of that and looking at it and just sort of seeing, like,
No.
I mean, just to confirm that your optimizer may have actually did it wrong here.
So a coarse grid search is how often, it's the standard way of setting up an interpolation on a surface. But if you do a coarse grid search, basically drop a grid and then look locally around some points, right? What you end up,
Well, I'm saying, or if you can bound it, which I guess is a whole other question, but assuming you can bound it, then you can.
there's, you're talking low dimensional problems, right?
Yeah.
So, you know, Mystic is designed to help with this, and that's why I'm saying modern optimization methods. It treats optimization, instead of a black box, as a white box, where you now have an experiment, you have a place to do analysis on your runs. Instead of getting a result, you go in and say, I need to be able to change, modify, test, verify, et cetera. Right? So some of the time what you'll get is logs, and I've been doing an optimization a long time. You get to know what a good trajectory looks like. I'll show you what a trajectory looks like in a minute, but you'll get to know what a good trajectory looks like. You get to trust things like, oh, there were lots of function evaluations this time as opposed to the last 6 times I ran it, so this is a better run. Convergence properties are smoother. It's an asymptotic convergence as opposed to it just stopped. Black magic, like I said, right? That used to be the case and still is the case for many people who do optimization. And like I said, in part, Mystic is trying to make a push to open that up to like real science, essentially, as opposed to trust. But this is a good case. People will say that this Rosenbrock is a good test function and is solvable by fmin and fmin-pal. And here we can see that it is solvable by fmin and fmin-pal 60% of the time. So if you're running an optimization, you should be careful. There, again, eyeball, number 1, and 2, multiple runs are both good diagnostics. I'll talk about some other diagnostics a little bit later. Okay, so here's penalty functions. Penalty functions are another fairly typical piece that come inside of some optimizers. So let's say you have something like this. Minimize or maximize a function. Here's our function. It's basically a function of two variables, x naught and x1. It's subject to constraints. A constraint of x cubed minus x1 is 0, and also a bounds constraint of x1 is always greater than or equal to 1. So basically what we've seen thus far, none of those optimizers can handle that. And in general, most optimizers can't handle it. This problem is not solvable with most optimizers, except for specialized optimizers who take penalty functions, and those tend to be linear programming, mixed integer programming, and quadratic programming optimizers, which are in general. So if you're in finance and you're predicting the stock market, you use LP and QP, which is essentially treat the stock market as if it were a line extrapolating out linearly, or at worst, some sort of parabolic shape. And that's it, because any of the other optimizers they use for prediction can't handle the constraints they want to use. Right? So you either have to use, what I mean by integer programming is we're working on the set of integers. What I mean by linear programming is we're working on linear fit, right? So this has x naught and x1, and basically you could, this isn't a linear problem, but if the fit is ax, it's a system of equations where it's ax plus b is 0, that's a linear fit. Now quadratic, of course, is one dimension up. Okay, so here's our objective, and we happen to have the derivative in this case, and then we chuck this into SciPy optimize with our initial, here, always the function. Here's our initial points. It's two-dimensional. We're additionally passing args, so SciPy optimize allows you to pass an additional arg to the objective. You notice our objective takes sign, which says, am I going to be positive or negative? That allows you to minimize or maximize. So this args basically applies anything that's not this first vector that the optimizer needs. Here's the Jacobian. Here's the method we're explicitly saying use the quadratic, QP, quadratic programming, and then basically get our result object. Now, here's our constraints. So these are penalty constraints, and these are, like I said, most optimizers can't do anything more than bounds constraints, except for these linear and quadratic programming optimizers, which allow you to take some very simple functions, which look just like the equations, okay? And what they do is they essentially, instead of solving an optimization on a function, they solve a system of equations first, basically. So that, let me see if I can get both of them in the picture. Okay. See, the function says x naught cubed minus x1 equals 0. And there's the first subject 2. Okay, so you basically directly put the, it's all of these constrained optimizers with penalty functions they work on equality constraints and inequality constraints. So we're providing the equality constraint and the equality constraints derivative and the inequality constraint and the inequality constraints derivative. And they're always balanced against the variables and equals 0 or greater than equals 0. Right? So if you have a less than equals 4, you got to put the 4 on the other side and flip the sign. So it's always equals to 0 or greater than equals to 0, equality and inequality constraints. And that is pretty much across the board for any penalty optimizer is going to be doing the same thing. Okay, and we, this first bit up here, it says unconstrained. We didn't provide the constraints. And down here we did. We say constraints is cons, and then run it again. And the thing I got the first time was it got the wrong value because it wasn't paying respect to the constraints, but now this one respected the constraints, and we got our solution we were looking for. If I was to run this 10 times, I would not get the same result every time, I'm pretty sure. Which is always a good check to do. Unless, of course, you can't afford to run it 10 times. Okay, so I wanted to go through a few of these these are the most common optimizers, and I wanted to kind of make the point of, these are most of the optimizers in SciPy Optimize. There are a few of them that aren't listed here. Like I said, the random forest is a newer one. Particle swarm is not necessarily a newer one, but it's newer, not very newer. It's not. It's the old new thing. And SciPy Optimize doesn't have it yet, but here is a list of the most common optimization algorithms. There's Nedler, Mead, and Powell, and basically it gives you a summary. I pulled it right out of the documentation if you do help on the module. And there's a short summary of all of them, but if you look at unconstrained, it's the bulk of them. Right? All sort of different variants on optimization, but they can't handle constraints. Constraint minimization, there are essentially 4. BFGS, the truncated Newton, Coblia, and this SLSQP. So each of those are geared for a particular kind of situation. And if you're trying to solve a problem that's a constrained problem that's not geared for that situation, then maybe your optimizer is configured to look for the wrong things in the determination. So what people do when they build optimization algorithms is they come up with a use case for it, and they bake in the most likely settings on the knobs to provide an answer for by default with those settings, so they don't have to be fiddled with for that particular class of problem that optimizer is geared for. And if you have something that's slightly different, most likely you won't get a good answer unless you go in and tweak the knobs. So that's another frustrating bit about optimizers, is that essentially, unless you have the problem that the optimizer is built for, you have to turn the knobs. You have to change the settings, and maybe it won't even work for you. Yes. In general, no. There are ways that you can do it in Python. If you build, if it depends on your algorithm, right? So if you can add a data descriptor, and if your data descriptor stays alive while the optimizer steps on it, basically, it doesn't convert it to a new object during the course of the optimization, then you can apply a constraint, whatever type of constraint you like. However, if the optimizer changes it to a different object, then you're out of luck. Mystic does some of that, but I will we'll come back to that point. It is possible to handle constraints generally in any case if you build them into your optimizer. If you build them into your objective function. What that means is if you have an objective function and you decide that what you're going to do is couple your objective function to your constraints function, then you can do it. And that might mean results come in and you decide, hey, if it's past, if the constraints fail, then throw a penalty on it. Basically, say the value is positive infinity, right? If the constraints fail, the value of the objective returns is not being called by the function, but what you get back is positive infinity. That's what I used to do. And that basically means that if you have constraint violation that happens infrequently, it works really well. Because then you'll go, and if it goes across the barrier where the constraints are bad, you get kicked back into the good region. But if you're looking at a needle in a haystack, basically what you then see is a completely flat surface, right? You get all bad violation of constraints, and it's flat, and your optimizer just stops. What I mean by that is if you always return the same value for being outside the constraints, you get a flat surface back. And what happens to an optimizer who is trying to find a minimum on a flat surface? It says, I'm done, right? So a penalty function, what penalty functions typically do, and that's what is built into those four, is it says, I look at how badly I've violated the constraint, and then I apply another function on top of the result I get from the objective function that adds a value. It perturbs the value. It doesn't apply a flat penalty. What it'll do is it'll apply like log, an inverse log over the amount it's deviating away beyond the barrier of the penalty. Right? So you'll have something like you look at what the constraint is, and if it's r squared past it, then apply a log function on top of the result you get back as a barrier. So what happens now is it has a way to roll off of that log function back towards the good region, and once it passes back into the good region, it drops down and no penalty is applied. So that is the standard technique to use for constraints optimization, is basically apply a penalty function. And that's actually the reason why that the standard thing is that you can't do more than 10 or so constraints on a problem. And if it's nonlinear constraints, it's even less. And that's because what happens is when you start applying penalty functions, several different, you apply a log function, you apply a inverse quadratic or something like that, you start applying a lot of penalty functions. What happens when you push a bunch of functions on top of each other and then sum the contributions from all those functions? You get now either something that looks like a flat surface or something that has a lot of surface features, which then optimizers will get stuck in. One penalty function being applied works well, two work okay. Once you start to get beyond that many constraints, it starts to become hard. And the only other way that optimizers solve the problem is to solve a system of linear equations as a matrix for the constraints plus the cost function, and then work on that solved system of constraints. So that is pretty much the box you will be in for any of the standard kind of optimization packages. So here is the a sampling of the linear programming, which have constrained programming choices in here, and also quadratic programming. These are very strongly used. There's a lot of other Python packages that are just generally linear programming and quadratic programming. CVX opt is one of them. Here is CVX opt. CVX opt basically is convex optimization. Convex optimization is a parabola, right? You have a parabola. So it gives linear and quadratic solvers, where instead of applying penalty functions, what it does is solve the system of equations first. And here now is several constraints on a system of two variables. And here we provide a matrix. There was 4 equations, so this is all the A values, this is all the B values. Let me try that again. Here's the first line, x naught, it's -1, 1, 0, and 1. -1, 1, -1. That's a -1 because that is the flip of the sign. -1, -1, 0, and 1. And this guy is 1, -1, 1, and -2. Right, so that's the A coefficient, and that's the B coefficient is a solution term. Solve the system of equations. Here's the cost, 2 and 1. Cost is basically our function up here. And then it goes. When you say solve, it's in this linear programming solver, where we give the cost function and then our A and B. And this one, it very nicely prints out a trail of the trajectory. Right? So what we get out of here is a trajectory plot that says, look at that, it looks like it converged, right? Which is not information we had before, and ultimately very helpful. It says it hops around, and then it's like 2.49, 2.4999, 2.5, 2.55. And believe me, that is something that is comforting to people who do optimization, to see this kind of semi-asymptotic behavior. They say, oh, I trust that. Okay. So other analysis terms here, but basically here's the y value and here's the x value, and here's the solution found are the two x values. And here's again constraint optimization with CVX opt, but doing quadratic programming. So there's, again, taking these guys, building matrix out of them, but it's essentially the same deal, where it's the coefficients of these matrices, but they look pretty much the same, and you get this nice trail. Again, notice how nice it is to get that trajectory instead of a single number. So basically, we can do that with SciPy Optimize. The new interface in SciPy Optimize doesn't really let you do it with this retal, retain all trajectories. But if we do the old SciPy Optimize interface, where we actually give the name of the optimizer and don't use the let it pick for you method, right? We basically, if we want to use Coblia, we have to say Coblia and use Coblia's interface. And we can say retal as retal equals true. And then it'll retain all of the trajectories in a NumPy array that it returns back, which is even nicer than having the printout, right? Then you actually have a trajectory that you can plot and look at by eye if you want, or do some analysis on about how the convergence behavior works or whatever. So if you'd like, to give it a try, you can take a whack at this problem, right, which is a constrained programming problem. If you can either do CVX opt or one of the SciPy constraint optimizers, it is a problem that should be solvable by either of them. It's one bounds constraint, the other is unbounded, two essentially inequality constraints and the function. And a lot of these optimizers pride themselves in being fast as opposed to being able to solve all sort of different flexible kind of problems. It essentially says, if you have a problem of the type that I solve, I'll do it fast for you. And if not, you can treat your problem like one of my problems and hey, best of luck to you. I'll give you an answer quickly. So that should say that there's a lot of problems in science that in the real world who one are not linear or quadratic, have many different constraints, nonlinear constraints, possibly, probably, and generally you need to know, or you'd like to know, the ultimate global minimum or global maximum, the extrema, as opposed to a local, and so we tend to have to work for global minimization and nonlinear equations, work with a global optimizer. There are not too many of those, and this is where more recent advances have come in. So one of the first is the differential evolution, which is a very, very robust method, but it tends to be very slow. So the most robust is the slowest. And what it does is it basically just randomly mutates a solution by, well, there's strategies to how it mutates a solution, but it gets a vector of solutions and then it changes a value. And then it may change two values or it may change another value as it goes through and iterates. And it generates a population of solutions. One of the reasons why it's slow and expensive is instead of doing let's say the simplex was like 4 balls and one at the center, like a top or something on wheels and kind of rolls like that would meanders down a surface. Differential evolution and some of these probabilistic optimizers, what they do is they say, oh, I have a population of 40. So that's 40 evaluations of the objective function. And I'm going to take the current best set of parameters that you have and tweak one of the values with some change, right? So if you have 1, 1, 1, 1, it might be 1, 1, 1, 1.5. And another one will have maybe the same value, maybe randomly changed. And what it does is just hopes that one of those values is better, and in general, it's not. So a common trajectory for a differential evolution is you have a couple choices where the random cloud is essentially finding some good bowl to fall into, and it starts to go into this ball, into this bowl, and then the choices become more limited. It finds randomly the improvement is harder to come by, and so what you get is the trajectories will be flat, basically no improvement, and then it'll start to improve again when it finds something good by chance, and then it'll tail off and it'll start to get flat again, and it'll go when it finds something good. Unfortunately, that period where it's not finding anything, if your settings for the optimizer are such that ahead of time you said, well, you know, it's really expensive to wait 500 iterations for an improvement, so I'm only going to wait 50 iterations for an improvement. Well, if the 51st one comes along, your optimizer stops, and you've not made it all the way down, right? So these guys become, how robust do you want to be? How long do you have to wait till you get the answer, basically? If your problem is expensive, then you can wait for a long time. But if it's not expensive, you might as well do a risk analysis before you run these things on how long you're going to wait. Some basin hopping is essentially similar algorithm to differential evolution with a different mutation strategy. And annealing is, again, it's a stochastic optimizer, but it's basically the process of, if you think about heating and cooling, it involves cooling towards a minimum and then heating back up to, by adding randomness essentially, and then cooling down and then heating back up. So it tries to hop out of a well through going uphill a little bit. So there's like a couple other techniques. Particle swarm is essentially just you have a whole bunch of explorers that go out, and the explorers that are finding the good wells, the other explorers say, hey, I should follow that guy, but not too closely. And then they kind of swarm around the minima, and then if somebody swarms off into another good area, then the swarm then will follow. Those are pretty advanced techniques, and the problem is, again, for nonlinear optimizers, they tend not to be constrained, so no constraints work, basically, and they tend to run a very long time. So here is differential evolution. Differential evolution, we're going to run it on the Rosenbrock function for 5 dimensions with here. This, when I'm saying bounds, so they take range constraints, right? They take box constraints. So I'm giving it box constraints. And I'm constraining it between -10 and 10 everywhere. So I'm making a little tiny box for it, which it should do decent at. And it's going to try to solve it within this little tiny box. And I do it 10 times, and it works 9 out of the 10 times. Look at the number of function evaluations as opposed to numbers like 63 that we were seeing before. Okay? Imagine if you're running again, you're trying to do molecular dynamics, and you're trying to find the best configuration for the parameter, for the properties that you see in your spectra. And your molecular dynamics calculation is a several hour calculation. That's not good. And again, it's not reliable either. No guarantees, right? The only way to make it more reliable, differential evolution will give you the right answer if you wait forever. But if you decide to shortchange it, then you may not always get the right answer. All right. So there are, basically those are our different types. And there's one specific special case that's worth mentioning, and that specific special case is least squared, wherever you went. There we go, least squared fitting, where least squared fitting is slightly different as far as what it takes. So far we've seen an optimization where an optimizer takes a function, and we're trying to solve the x value of that function by looking at an energy surface, the y values, to get to the minimum. In least squared, the target is fitting to data. The target's fitting to data. So the least squared minimizers are phrased slightly differently. You see down at the bottom, curve fit, where it takes a function. But what it does, it takes a function, it takes x, it takes our data, which I'm calling noisy, and then it takes an initial guess, not on x. It takes an initial guess on the parameters, where the parameters are a, b, f, and phi. So what we're doing is now thinking about fitting something like a polynomial, fitting a specific function to your data, where the things that you want to fit is not the form of the function. You want to fit the parameters, the fit parameters, basically, of the function. So a, b, f, and phi. That's our goal here, is to fit that to the data. So you see the additional thing that we're bringing in is fitting that function against the data over the range of x, and then we're solving for the optimal set of parameters, p naught. And what you get back from any good least squared, because of the technique, is you get the fit of the parameters, your best fit of the parameters, and you get a covariance matrix back. You get error estimate back as well, which is nice. You can see how basically the parameters relate to one another. You can see whether if it's a strongly diagonal matrix, basically, good job. If it's not a strongly diagonal matrix, then you have parameter mixing. Essentially, they're not independent of each other. So this just little bit here is creating Gaussian noise around the actual parameters. And here, what you want to do is check the diagonal. If the diagonal is a lot of ones, you're in good shape. So here I plot, and I can see our target parameters were 3, 2, 1, and 0.7, and I got back almost 3, almost 2, almost 1, and I did pretty good. The last one's a little bit off, and you can see that in the covariance. It's a little bit higher here. This is actually a little bit higher too, but it's not bad. It looks like the fit works pretty well. It's probably not so good right about here, where there's a sparsity of points. So people do a lot of things for least squared. They will do things like, since what you're actually doing is fitting to data points, and maybe in a sparsity of points, what it says is the function should look like that, when you know it actually doesn't, right? If you just track the data points, it's trying to fit. So the fit function for that parameter shape best fits this jagged function between the points. A lot of people will smooth their data first to do an actual kind of interpolation on the points, and come up with a function that represents their data, and then fit to that function. Sometimes that works better. What kind of effects does it introduce? It's a standard technique.
I mean, the benefit is that you're less likely to overfit that way.
The benefit is you're less likely to overfit, but you're more likely to bias your results. That's right. That's right. Again, I'm just talking about this is the standard. This is how optimization has been done, and is still done by the majority of people. So typical uses, we talked about function minimization, data fitting. Data fitting I just showed up here, but actually you can use any optimizer to do data fitting, right? Any optimizer can do data fitting. simply to get data fitting out of any optimizer, what would you need to do? Area under the curve, right? It's basically the difference between the objective function and your data points. If you look at minimizing the difference between your objective function and the data points, you're doing a curve fit. So you don't necessarily have to use the least squared optimizer. The least squared optimizer is built for that, and therefore it gives you the nice covariance matrix at the end. It's geared to optimizing the parameters, but you could do it with any optimizer. All right. Root finding is another one. Here is another common thing with optimizers. Here's root, which is particularly geared for root finding. And you have a system of equations, again, additional parameters. X, which is a vector, and then A, B, and C. And here's our system of equations. It's implicit that they sum to 0. So this would be our first equation equals 0, our second equation equals 0, and our third equation equals 0. Root finding tends not to work for inequalities. So if you have an inequality in there, you treat it as if it were not an inequality, which can often lead to bad results. So here's our system, and the goal is, because they all sum to 0, we're going to try to find the value where this system returns a 0, right? We're essentially looking to find where the value returned here by our objective is 0, therefore satisfying the system of equations. And then what we have is our coefficients, which are set. The coefficients are passed in as extra args, and we essentially do just the standard optimization on our system of equations for x, and we get a result back of our solved x. Result x is our roots of the equation, and the solution, we should get back 0. If we don't get back 0, we know we don't have the right answer. All right, so there are some optimizers that are geared for that, but in general, you can do that with any optimizer as well. So there's parameter estimation, which is essentially just like the cases that we've also seen, except we might be geared like this one is for polynomial fitting. And this is generally used for fitting to data as well, as you have we're creating some noisy data. We have some noisy data. We have x values and noisy data on the y, and we're fitting a first order linear polynomial where we get the coefficients back. That's the best linear fit to it. And then we build a polynomial object, which we saw before. Then we can plot and print out nicely. So this will give you a linear fit. That will give you a quadratic fit. Underneath, it's calling not a global optimizer. It's calling a steepest descent optimizer or gradient optimizer. Sorry, gradient optimizer. So if we ran this a number of times and printed out the results, they would also give you a slightly different fit. So you're not guaranteed to get the same polynomial fit every time either. And this is just fitting a line to a bunch of data points. I see a lot of unhappy faces. This is optimization. Okay, so here is a coverage of the standard diagnostic tools we've seen so far, and these are it, essentially. Eyeball is number one. Run it several times and take the best result. That's also confidence building, right? Get a log of the intermediate results, basically the trajectory. Look at the trajectory, look at the shape of the trajectory. Does it look nice? Right? Does it look like it goes somewhere with intent as opposed to just stopping? And every once in a while, some optimizers will give you the covariance matrix. The question you should have for yourself is, how can you be really sure you have the results you're looking for, right? How do you know you're right? Now, I have this as part of what I may get to and may not get to, but what you can do is if there are some recent theories on statistics that are in the domain of uncertainty quantification, and basically what they do are phrase probabilistic problems, stochastic problems, in terms of optimization problems. And if you want to then try to validate your optimization, does it give you the right value? What's the likelihood you have the right value? You can then run a optimization problem on top of that optimization problem to verify that you're actually getting the right results. Although unfortunately, you're running an optimization problem, which then you may not have the right results for, and you'd have to check ad infinitum. The good thing though is most, no matter the complexity, so if you're doing a very nasty oceanographic, or climate simulation, which has tons of nonlinear parameters and equations, the UQ, the uncertainty quantification optimization on top of it is actually convex. So those tend to be nicer and they tend to converge better. So the optimization underneath is ugly and unreliable in many regards. But the phrase of a likelihood, which is just linear or quadratic. I can, if I don't get to cover that part of it, I can at least point you to how to do that. The problem is those things become expensive because now you're running the thing you wanted to optimize maybe 100 or 2,000 times, right? So you usually need big computing systems to do it. Yeah.
Because it seems to me like looking at the trajectory, I mean, you could have a really nice looking trajectory and still
Go to the wrong place.
false minimum.
That's right. So the only thing the trajectory is going to do for you is tell you that smoothness of it says, I probably found a minima. Whether it's the global minima or not, you don't know. Well, so that behaves differently. Spoken like someone who's done this a lot, right? So if you're at a plateau, plateaus go and they die differently.
Oh, because you keep drifting.
That's
You don't-
right.
You don't keep drifting back.
Yeah, so you get this nice asymptotic behavior where the change delta comes down, la 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 la, as opposed to something that just goes dead, right? When it gets stuck somewhere in a point that's not a minima, but it gets trapped in the algorithmic response, essentially you get it just go and it over very abruptly, and those are always bad, unless you get lucky when it actually hops into the minima and finds the right value, and then you'll disregard the point usually. This is not how we operate as scientists, right? We don't want to operate like this, but this is how optimization forces us to operate in many regards.
Particularly if you don't have the time to dig into the whole world of like how does the math level of certain things work.
Yeah,
Well, I mean, the problem is that actually global minimization is actually an uncomputable problem. I mean, imagine even in 1D, you've got a function, it's got nice smooth wells, you've got a global
So there, one of the reasons why I have been, over the past several years, pushing an algorithmic shift, me and a few others, in how to do optimization, not only in making it more transparent computationally, computer science-wise, but using parallel computing to change the paradigm for how people do nonlinear and constraint optimization. So we're almost to the point where we'll start to look at that. So I think if you'd like, take a look at any of the solvers that we've done this far, and try it against the Zimmerman function. Zimmerman function is found in Mystic. Mystic models Zimmerman. And essentially, if you want to look at the Mystic model plotter, that's always a good way to start, in that you basically get a good picture of what the Zimmerman function looks like. You can look at the documentation to look at models Zimmerman doc, and you could see what it looks like. The thing it looks like is, and that gives you the hint how to run it in the model plotter. It gives you, the function is essentially a function that has, well, if you plot it, you'll see it. It has, it was a function that was constrained, that this is what it takes to apply constraints to a function, rewriting, in many cases, the function itself, so the constraints are baked into the objective. That's what was done, and it was still a hard minimization for many of the optimizers. So if you'd like to do that, try the Zimmerman on any of the optimization algorithms we've seen this far. It has a, here at the documentation, which will tell you, it has a minima at 7 and 2. And if you'd rather, instead of the Zimmerman, you can also do the FOSC3D function, which is also found in Mystic. You do the same thing. Basically, any of these things where it shows the bounds, feel free, if you're using a bounds constrained optimizer, to use those as bounds. So you have those two. And I think if this works, since we're getting towards the middle break part of the thing, right? What I'll do is take a break now if you want, take a break after you've worked on these if you want, and we'll essentially just take 15 minutes plus the time to fiddle around with these a little bit, and call that either the time you want to fiddle around with them longer, or the time you want to take a break longer. So I'll start back up at 15 plus a little bit. I was talking about what a good trajectory looks like. I look at this, and you can kind of see how this is differential evolution, and how it's kind of zeroing out slowly at basically the same rate. It has a little jump every once in a while, but it's basically slowly stretching out, and then eventually goes off to zero. So that looks good, in that as the numbers go thinner, the time it takes between the next jump is also longer. I would look at that log, and I would look at those numbers being printed out there and say, I probably have a winner. But of course, it is possible to do better. I would scale this, but this is the path that the thing took. The black line with differential evolution. So let me scale it. And it indeed did go to the right place. It actually did pretty well, right? It just hung around in the area that's the sieve and then kind of made its way down the one end. I was confident in it when I saw the thing printed out on screen, but this is pretty good too. Right, so now I cheated because I used Mystic, and I have a little bit more, I have a little bit more knobs to turn in those than you guys probably had, but people were able to find some solutions, find that corner, feel confident they were in the right place with what they tried so far on the Zimmerman function. What I wanted you to do with the Zimmerman function is basically, if you haven't done optimization thus far, or if you've tried it a little bit, you shouldn't get discouraged about it not working, right? It just means you've got to work a little bit harder. You've got to turn the knobs. And what I mean by turn the knobs are there are things for each algorithm you're going to be using that you have to learn to apply. Things like the X tolerance for the convergence criteria. So really one of the things that I found in going in and abstracting the algorithms like I did in Mystic is that what Mystic does is it removes the termination conditions from the optimization algorithm and says you can set them to whatever you want. Okay? It basically tears apart the optimization algorithms into their component pieces and lets them be configurable. And that way, you're not working off the best termination condition for a particular type of thing that the optimization algorithm was designed for. You can change the termination condition to be whatever that you're looking for. So if you know your case is that you're going to have a steep gradients, maybe you want to always work off the gradient. You want to have a convergence that says, well, if the gradient levels out over a certain time and is not changing, that's the thing I want to key off of, as opposed to getting below a certain value or something like that. So a very simple termination condition is if you get below 0, it stops. Right? Or if you roll past n number of optimizations, it stops. So there's things like that. Another one is you haven't had a change to the gradient in some tolerance over X number of parameters. So you have an idea of what your surface looks like. You should be able to tweak those things. But in most cases, the optimization algorithms, what they do outside of Mystic, what they do is traditionally is they just say, well, I have 1 or 2 parameters that you can tweak a little bit to change slightly how the termination condition is going to happen. But it doesn't allow you to change them wholesale, which you should be able to do. Okay. So people successful with fiddling knobs and finding Zimmerman? I mean, this is what this is what it looks like in Mystic Differential Evolution Solver, random initial points. I didn't play with the settings too much. I just said stop after n number of generations. Put a monitor on it that's going to produce a log. It's going to print out the stuff to the screen, and it's going to write a trajectory log. It's going to do it at one iteration recorded in a log and one iteration recorded on the screen. And then I solve the cost function. Here I changed the termination condition and customized the strategy and the mutation strategy of the optimizer. These are knobs, as I would call them. And this is essentially the thing, termination condition, that basically VTR says there's a basement, and if you get under this value, then quit. So this particular optimizer, differential evolution, would just run forever and not quit until it got under that value, or it reached the maximum number of iterations, which is better than most differential evolution algorithms where you have to say stop after you don't get a new change after 50 points or 100 points or whatever. Right? Because then what happens if you find the actual global minimum in 3 steps, you've still got to wait that 50 or 100 that you've set before the actual thing stops. Okay, so we'll see more of what it looks like in Mystic later, but that at least gives you some exposure to going in there and monkeying with those things a little bit. All right. What number is that? Okay, misspelling will not help. The solution for what I just did for Zimmerman? Yeah, that would this is my solution for Zimmerman. The FOSC 3D. I could just drop the same thing in. The difference, really, the solution there is you've got enough experience to play with the knobs. So if you ran it and you're lucky enough for it that you picked an algorithm that succeeds, then you didn't get as much experience as if you picked one that struggles at it and you have to fight with some of the settings. But so that's what the solution looks like. Okay, so here's a optimization with Mystic. I just showed you very quickly a little bit of what that looks like. Obviously, again, from up here, it has a class instance interface. So it's an instance of a solver, but it also has a one-liner interface. And I'll start there. So Mystic approximates basically the SciPy optimized interface, which is a Python standard. And here is a taking fmin on Rosen for some initial condition. We're going to give it retol to give all the trajectories out when we're done, and we get our solution, where our solution is an object basically composed of the x vectors and the y vectors and some other diagnostics that you can also get in the results object. So it's a pre-results object. And I look at all my vectors, I can plot all my vectors. So here is I1 for I in all vectors, I of 0 for I in all vectors, I1 for I in all vectors, and I2 for I in all vectors. And that's basically a plot of all the trajectories in solving that problem. And so here now is a plot of how the parameters converged individually, as if we were going to track the x values and the y value. So that is even better. So now you saw Mystic already provides the plot, and you saw it provides the trajectory as a path on the plot. But you can also look at trajectory in this way. And this, again, basically tells me that I very likely have found a minima, not necessarily the global minima, but a minima. Right? It's a nice, smooth convergence to a point. So it's more information. And again, if you go back and think of it as an optimizer as an instrument, we have to run a lot of experiments, and this is getting more diagnostic information. All right, so that is doing that. Let's look at more diagnostic tools. Well, one of the things you can do with the diagnostic tool is Mystic provides callbacks. So this is one of them that I think I'm not going to run in IPython because IPython doesn't handle interactivity at the shell very well during a notebook. It tends to hang IPython. So you can run this at the command prompt, but Mystic allows you to interrupt solver progress. If the solver's running and you give it a handler, if you give it an event handler or a signal handler, it can catch a kill signal from the prompt. Or if you have an event handler, it can catch an event and interrupt the solver and provide a very minimal shell that then you can say, I want to do something. I want to call the callback. I want to quit. I want to get the current best value. So I encourage you, if you download this to a file and run it on the command line, it'll do a lot better than hanging your IPython. Well, IPython hanging on it. But the point, as well as here's a handler. You just say handler is true, and that gives you the signal handler, which responds to Control C as it's running. And here's a callback. And the function that I'm registering in the callback is plot params, which gives you the same trajectory plot that I just showed. So let me get the shell out. And which one is this? Python 4, I think. Yep. Okay. There we go. And that's the callback function being used. I didn't interrupt it, but so what I did was I registered the plot. I registered that plotting method that we used at the end to do the analysis of the trajectories as my callback. So it's going to be expensive, but every iteration, it basically adds to the plot. You can do something different. You can, like I said, if the thing that's important for you is the derivative, then you can have it do a derivative estimation at the end of every iteration. Or if there's a certain parameter that you need to check, you can do that. It has a somewhat limited functional interface. It basically requires a function of x. So you have to have plot params as a function of x. No additional args. All right, so here's a different callback function I'm registering. Essentially exactly the same thing as above, where exactly the same thing as above. Matter of fact, it just pulls from that file. And when I run it, what I'm registering is print params. So instead of plotting the parameters, it's going to print the parameters, where print params looks like this. Basically says generation blah has the best fit blah of iter and an array of the parameters. And that'll look like that will look like this printout, which we've seen already. That's a dumbed down version, one of my original versions of what the monitors look like. So you can make your own monitor, you can make your own callback function, whatever. It just has to take a function of one variable, and you can hook it up and have it called at every iteration. So that gives some diagnostic. Now there are monitor objects which actually are configurable class instances where these guys, there's different flavors of monitor objects. You can build your own monitor object. You can just derive from the base monitor object and build your own. But I give a verbose monitor, which prints results to the screen. I give a logging monitor, which builds a trajectory file. I give a verbose logging monitor, which does both. And I think that's all the standard variants. Basically gives you the ability to log to a file and print to the screen, or one or the other. And what you do is you build an instance of the monitor and then pass it in as either the iteration monitor or the step monitor. So do you want to track every function evaluation? Do you want to have a plot of every function evaluation? Do you want to have diagnostics on every point that was called and keep it? That's not useful for a lot of things, but if you're doing surface interpolation, it's very useful. If you're looking at trajectories, you probably want to only maintain the iterations. If you're just trying to get to the minimum, then the iterations are nice. So what that does is it runs and it populates the step monitor instance here. So it doesn't munge the step monitor, and you basically get it populated back to this object. Although the result object, you can get the step monitor back from any solver. I could say fminpal and then pop out the result monitor out of it. I'll show that later. But that's what a typical verbose monitor looks like. And the verbose logging monitor will, so I should run this. Okay. Okay, so that's the run, and then when I run the log reader, it basically pops up this guy, which is a simple trajectory plot. And these guys are, this is configurable, but this is the trajectory plot, and this is the cost. And it basically runs off of the log, which was dumped by the monitor, and allows you to dive into these things and see, again, visually what happened. It kind of looks funky because, well, there's only 14 points that were dumped to it, right? This was a pretty easy optimization. They can have much more shape and texture than that, and they can have a lot more points. But that gives you a nice picture. And then again, having the run on the model plotter can use the same pictorial representation, and here's the trajectory plotted on the model plotter. It was a pretty easy one. That's why it only took 14 points. I started up here, and it basically went right down the well. Okay? And that runs off the same log file. All right, so solver tuning basically Mystic provides, as we saw, a functional interface like SciPy. These are the same algorithms, but with a lot more flexibility built into the algorithm, and it's exposed as keywords like itermon, which is the step monitor. And also things like interruptibility, like I was showing, and callbacks. We can use the class interface, which is basically underneath the function interface. And the class interface says, I want an instance of a differential evolution solver. I'm going to take a Chebyshev polynomial, a 8th order Chebyshev polynomial. I'm going to pick my termination condition. I'm going to pick my strategy that is a randomization strategy. This is best one exp, where it's only taking the best one value as opposed to the best two or the next best two or something like that. And I'm attaching a verbose monitor, so no logs, just printed to the screen. And basically a bunch of plots. What you end up doing is building the solver with the number of dimensions and the size of the population for the differential evolution solver. So I don't even remember what the default is anymore. 10, maybe 4, something like that. Something fast. I picked, in this case, 10 times the number of dimensions, so there should be 30 or 40, whatever it is. And then I configure the initial population. So basically, all optimization algorithms, they fall into actually several pieces. We talked about constraints and these kind of things before, but we didn't actually break down the optimization algorithm. And breaking down the optimization algorithm, you break it down into setting up the initial population that you work over. It could be an initial point, it could be a simplex around a point, or it could be a distribution, or it could be a swarm. So all of those things you should be able to configure. You should be able to say, I want to sample out of random uniform or multivariate uniform points to fill my population. So you can configure that with Mystic's. So citing an optimizer becomes more difficult, right? You actually have to cite the settings it's not just a flat optimizer anymore. It's not differential evolution. It's differential evolution with this particular type of population, with this particular termination condition. So you can also change the termination condition. Here I'm using VTR again, which basically says I want to run differential evolution where it doesn't die after a particular time until it gets below a value that I consider to be low enough, which is fairly useful. So, and I have the callback, which is to plot the solution. All right, so then that would do that. You can then solve the problem, and then to get the answer out, you can do solve or solution, and you'll get the x values out. You can also get that at out of the monitor, or you could get it out of solver.best solution, which is, I believe, the older interface, which is still in there. Here's a step monitor. You can see the length of the step monitor to get the number of iterations, or you can get that directly off the solver. You can ask for solver generations, and it'll give you the number of iterations that you've run. The X and Y are the X and Y of the step monitor will actually reach into the monitor and give you the trajectory values of X and Y. X being the parameters and Y being the energy. And then you can go and plot these things afterward, plot the trajectories. So it gives you easy access to the trajectories. Here is 8th order Chebyshev polynomial, optimized basically at those settings with differential evolution. You get a pretty damn good fit. And this is one of those that's interruptible, I believe. I may have took that out for this example. But if you hook up the plot function here to it, you run it, you interrupt it, you'll get a current plot of what the current value looks like. And when we continue, it'll keep going. So you can get a picture of kind of how close am I right now. Because monitors are populated with pointers, you can actually look at the monitors at any time. You can make a plot like those solution plots that I have showed at the end with the trajectories on the surface. I can, if the log plot is being written to file, then I can just look at that and watch the trajectory go down the surface, or plot it so I can see where the results are going. And if it looks like it's going awry, especially awry for the flexibility that I know that the algorithm has built into it for the optimizer, then I can just interrupt it and stop. So interactivity with the solver is good, especially when you start to see, poor behavior in what your trajectories look like. And what you start to learn to do to diagnose is you look at a picture of what of maybe a slice of what your objective looks like, and then what your current solution looks like, and then look at certain diagnostics on the trajectories and the cost of, is the cost margin not changing very much? Is the trajectory rough or looking funny? And if it is, I'm probably wasting my time on this one, which tends to be the case for killing these things. So if you look at these, this is the this is all the methods that are available on the optimizer that I just dumped out, basically. So there's a lot of things that are available. I'm not going to go through all of them, but they're in the documentation. And there's basically things like set the penalty, so set a penalty function, set termination conditions, set the constraints. Penalty functions, in Mystic, penalty functions and constraints are different things. And I get to draw on the board for this. F of x plus p of x is y. This is your cost function. That's a penalty. You see, it's a perturbation on it, right? And y is f of c of x. call a constraint or a constraint operator, where the constraint operator can make f of x prime, or it can make f of prime of x. And that essentially constrains, it reduces f's space, or it reduces x's space. So you get a mathematical map, a mapping of space to reduce the search space of the optimizer. So for me, that is what I call a constraint. That is different than the penalty function, which is like the first one. Yeah. Yes. So the optimizer, essentially, the objective function will only ever see valid points. It'll only ever see valid points. An optimizer always picks in a box, which is why they have box constraints. And I take that box and I transform it into the valid space for the optimizer. And so when it picks in the box, it maps to a valid point for the optimizer through a mathematical transformation of space. Not a filter. You can make a filter if you like, but it's a spatial transformation. So you always pick points that satisfy the constraints. So that's constraints. So there's box constraints, which are right here, set strict ranges. Okay, so that is how I set box constraints. So there's all sort of different, you can see there's a lot of different methods for tuning your solver, and all of those have different settings on them. Another one that's useful is save solver and load solver. There's also step and terminated, which are different. So step and terminated, actually all my solvers are asynchronous, and they're iterable. You can iterate, you can move asynchronously and iterate through an optimization algorithm a step at a time, which is useful in that what you can do is then take your best fit, take the algorithm which is at the best point, have it go one step, but have that one step where you've replicated that optimizer on 100 different processors. It runs that one best step with the random seed that's different on each of those different processors, comes back with the values, and you can pick the best one or whatever your meta algorithm you're building on top of that is. Right? So then you can take a simple steepest descent algorithm and give it a huge population that it's going to be working with. When you inject some randomness, come back and turn it into a super massively parallel kind of differential evolution kind of idea. Essentially, the solvers are fully pickable, so you can save the state and ship it off somewhere, and then load it back up as an object. One of the things we can change is the termination conditions. So here you can set, there's a lot of different termination conditions, and there's a mini language around termination conditions. So here I have VTR, which is basically cut off after a plateau is reached of an energy plateau, and then changeover generation, which is the default that differential evolution has, right? If you don't have a new change within some delta over n generations, then stop. Well, so what I've done there is I've built a termination condition that says I want both of those, and VTR, the default value for VTR, the default value for changeover generations. So I want both of those to be satisfied before I stop, or VTR at 1 e to the minus 8. Okay, so I have when, and, or, and not. And you can make compound termination conditions. Another termination condition is the number of times the thing's been called, things like that. I don't have time as in wall clock time, but it would be easy to build. Right? These are fairly simple functions, and you could build one if you're interested in doing that. And so if you're looking for something really specific and you know what your solution is supposed to look like, you just don't know where it is, customize your termination condition. Mystic does not have a lot of optimizers in the classical sense because it's so configurable on the things that really matter. Termination conditions is one of the big ones. Is when if you're working with a robust optimizer or a completely not robust optimizer, it's more important of saying, well, when should I stop? When is my answer, right? That's a matter of finding what you're looking for. So this is telling Mystic what you're looking for. Not how to get there, but what you're looking for. You could do a gradient termination condition where a parameter has a particular value if you wanted. All of those things are possible to have added in there. And here's it being set up to take strict ranges. So this is -10 to 10, -10 to 10, and -10 to 10, which is the same as the bounds on my random initial points, picking between -10 and 10. There's my termination condition. And this is an additional termination condition, which, because it's called so frequently, I leave it to be called independently, and it gets packed in with the other termination condition with an and, or an or, with an or. Set evaluation limit, so only run up to 600 times. And then you get a run like this, and this says, aha, I stopped with this termination condition. So that was the or value and not the and value. And what you'll find is if you run it several times, it's differential evolution. Sometimes you'll see any one of the three termination conditions that are involved there. The and, which will have both of them, and you won't know, well, which one came first, but it'll say both of them were satisfied. That actually writes to the log too, so you can see what's been satisfied. It's also saved in the state of the optimizer, so you can actually pull it out of the solver. You can ask solver terminated, and it'll tell you what the termination condition was. That's what terminated does. Okay, so yeah, so if you want to try to use Mystic, essentially, you could misspell minimum. You could try to find the minimum of the peaks test function with the bound specified, just like before in the documentation. And if you'd rather do a curve fit, use Mystic to fit the noisy data that was in the SciPy optimized curve fit problem. And again, what you would do to fit to a curve is probably going to be something like this. F of x minus g, where g is your data. And you want to come up with some metric of a fit. So people will often do something like that. Right? That's a fit where this would be your cost. Okay. and that would be fitting to your data. All right, so people somewhat successful in doing the fit to the data. The way this thing should be constructed to do a fit to the data is basically something of this regard. Something of this regard over here, where we have here's the function as we had it before. Here's our objective, where the objective takes an array, a vector of the parameters, and we then will take the function being evaluated on the x values at the current list of parameters minus the data. We have to get some metric, so I'm just using a difference metric where I've squared and then summed, right, to get a single value back. We can't get a list back. That's not a single value, so it's a sum of squares as our metric. And what you'll find is I'm finding that I do okay, but it's somewhat limited. And when I'm starting to keep running into the same hard value, then the next step is I would modify this slightly to maybe do a difference of squares or something like that. Change the metric. Changing this metric here changes the surface that you're optimizing over. So maybe the surface that I have here is not so easy to go over. But that would be my next step. So you want to build something that looks like that, where you can play with this metric. It's actually up to you on how you're accounting for the difference, what the distance to a surface is. So actually, Mystic has a module called distance, which basically gives you all sort of different distance formulations, anything from Chevy Chef norm, boxcar norm, all sort of different odd mathematical distance norms that you can use. All right, but even though that one wasn't doing that well, I was still getting in the ballpark of 2.7 and 2.1, and which are close to 3 and 2. Okay, so functional constraints. Now this is where Mystic changes a little bit. Is that idea of constraints? There's a constraints package and penalty, a penalty module and a constraints module on the inside. And I'm going to go through just basically, these are some constructs. This is part of my test environment. But basically, you can build things like this, which is calculate the mean constraint. I mean, this is a mean constraint, right? So it takes an x and it takes a target, which is your target mean. It takes the mean and it takes the distance from the mean. So basically, what you have is you're not imposing, but you're calculating the mean, and the mean difference, the difference of the mean and actual target value. So if you're going to impose a mean penalty, if you're going to impose a penalty, a stronger penalty is imposed, the further away the mean is from the target value, this would be the penalty method that you would build. Right? Here's a range constraint. I have a spread, which is the range of your points in a set. I have your target range value, and then if I were to build a penalty off of this, it would be penalizing on the distance away that the range is from the targeted value. This is good for statistical and probabilistic optimization, where we're looking at things like the mean of some expected value or the range of points in a collection. And then I can pick the type of penalty the type of penalty is a quadratic equality constraint. So a quadratic equality penalty, and I give it a condition. The first condition is a range constraint, where I'm going to then pass in keywords, so I don't have to hard code them. They're decorators, so they can both be applied. So this penalty function, a penalty of x, returns 0 penalty if none of those constraints have been violated. But if it has been violated, it imposes a penalty of quadratic. And it's an equality constraint, so that means the only place it's not violated is when it exactly matches the mean and the range. So this gives me a twofold application of the penalty onto the penalty function, and I've just built a penalty function that can now be passed into any optimizer. Any of the optimizers can take a penalty function. So all of the optimizers can take penalty function like this, where I can build it as I like. It's essentially customizable, where I can do quadratic inequality or one of the other penalty functions that I have or that you could build. There's my cost function, which is basically the absolute value of the sum of x minus 5. And it's penalized where it has to be the mean of x, and the mean of x is 5 and the range is 5. So you want to solve that problem, then it's this the f min. So I'm actually solving it with Nelder-Mead, a constrained optimization problem with basically set constraints, probabilistic constraints on a cost function, and then there's arbitrary penalties being added. So you can see the mean is found to be 5, the range is found to be 5, and the cost function gives you a value where you also get the 5, which is what we were looking for. This gives you a lot of the different formulations that you have. There's, again, quadratic inequality. I'm now looking at a parameter constraint as opposed to a mean constraint. So here is x, and what I want to do is I want to make sure that x1, the last x and the first x are the same value, right? You get a penalty if those values are different. So quadratic inequality for penalized anywhere that those values are different. And that's a way to bind two parameters to the same value. Okay. So here is a different type of constraint. This is with mean constraint of 1, where I want a parameter constraint to take x and return x. Now this is not targeted as a penalty function. This is targeted as a constraint, which is a mapping of space, that C operator. And those C penalty functions will take x values and return y's, where constraints or maps of space will take x values and return a modified set of x values. So this says I take the x values that were selected and I map the space so it fixes x1 to be x0. And then it returns me my x values, so I've just mapped the space. And it also does it where it's imposing a mean constraint of 1. There's a little bit of code there, so I've wrapped it into a decorator that you can use. And now when we solve this constraint, you could see that the value you would get here would actually be, I don't know where it is printed out at, but x does equal x1. It's a solution to those constraints, and the value of the solution is the mean is equal to 1 within a tolerance of 1e to the 15. So essentially what it's done is it's put it on the space where all of those values are true, and then it found the minimum within that reduced space. So you can see that it follows the same pattern. These are actually basically what working with the functional constraints and penalty functions look like, and they can be provided to any solver. So there's again the mean and range constraint. And then what I've done is I've built them as penalty functions. I built them as penalty functions just like I did before, and I've built the penalty function. But then let's say sometimes building a map is a hard thing to do. Building a penalty function is pretty easy. They're built just like the equations. All you have to do is say this value minus this value is 0. But to build a map, which is a mapping operator, is a little bit more complex. So say you don't want to work hard and do it, you can say, give me this penalty function as a constraint, and it'll convert it into a map of space. The only thing is, if you built the map by hand, it will be more efficient than if you let Mystic auto build it for you. Because what it'll do is it'll say, I need this function to be, unless I know the transformation, I'm going to do a brute force transformation, which means use a solver to ensure that it's been satisfied. So it can be very expensive. But it works if you can't logic through it, basically. All right, so here you can do the same thing. If you just so happen to have a very easy constraint function you're building, here's with the range and a mean constraint, then you can convert that to a penalty if you like, and then use that as a penalty. And there, let's see, you can do a lot of different bits of configurability. This one has a decorator. It's the mean of the squared of x. We're going to be constraining on the space of the mean of mean of x squared. And I will just skip to here. So here's a Rosenbrock's function with Powell's method, except what I'm going to be doing in this case is taking the mean of with the mean of 1. So on average, the value should equal 1. That is just happen to be where the minima is, and it's going to bound it around the minima, so it should work faster. I'm going to set the first parameter equal to the last parameter. That'll also help it since all the Rosenbrock parameters are equal. And this thing does just absolutely, even with differential evolution, is it differential evolution? No, F-min-Powell. It just goes straight to it, basically. 2 iterations, and it finds it pretty exactly. It's because I've really constrained the space to where the solution is. You can use, like I said before, set strict range to impose the box constraints, but I actually added also, if you want to give the constraints as matrices like CVX op, you can do that. Or if you'd like SciPy, you can write it as symbolic equations. So if you write it as a system of equations, and then you take these equations and you say generate your conditions, the conditions will give you inequality and equality functions, and then you can use those functions to generate a penalty or generate constraints. So what it does is essentially parse that code and turn it into a function so you don't have to do the programming. Here's a tension compression spring basically, where we're trying to solve for those values. And if you run the thing, you'll see it works. Basically, these are some pretty hairy constraints, right? That's actual real physics and engineering constraints. And the solver we're working on is differential evolution. So it's a nonlinear solver with nonlinear constrained space. Well, actually, I'm using it as a penalty function. But you can apply both penalties and constraints, and it tends to work with applying 1 or 2 penalties and then constraints, or you have to play with it, basically. So here's again some other nastiness. Here's the details of the steps being done. There is converted the symbolic equations to single constraints functions. And there's the printout of what that does. I'll show at the bottom. And then take all of the individual inequalities. You can look at what they are by looking at the documentation. So it encapsulates the symbolic equations as the documentation, so you know what they are. And then generate the penalty function from all the inequalities and equalities. So it's an all-in-one penalty. And the documentation also captures that. So you can see that here is what you get back from, this is generated for inequality constraints from the symbolic equations and no equality constraints. Here's what it says in the documentation. The doc string is essentially auto-built into the equation. And then when you do the penalty function, it lists the type of penalty plus the thing that's being penalized. So you know what you're working over. All right. And so this is nice, and I can take that symbolic expression, and if I wanted to, I could have built it like this. Penalty at a time where this equation is essentially penalized everywhere at less than or equal to 0, because there are quadratic inequality constraints I'm applying. So this equation, less than or equal to 0, is applied here, where I, again, have some tuning parameters that I can put on the quadratic inequality to affect the shape of the quadratic inequality that I'm applying, of the quadratic that I'm applying. And so I'm applying the penalty, and if I then wanted to build a constraint from it, then I can build a constraint directly from the penalty function. Again, this will be expensive because it's not an analytical path to it, algorithmic path to it. It's a brute force, but still. So that works. What you can end up doing is you're now turning nonlinear, non-convex problems with nonlinear constraints into constrained space problems over lower dimensions, so they're easier to solve, basically. So here's a problem from Google's constraint programming solver. It's basically, here's the solution up there, which is each letter of the alphabet is a number. And here's the equations, which if you'd like to go through and cryptographically translate, you could. But that's our system of equations. They're equality constraints, so they're even harder than the inequality constraints. And there's the list of variables, A through Z. We're going to cheat, basically, and say we know the vowels. I'm binding the vowels to a particular value. And then I go through and solve this 20-dimensional cryptographic problem over the space of the integers, right? So what this does is take the constraints, make sure they're integers by rounding and then converting it to an integer type, and then clipping off to impose the bounds of we don't want the values to be less than 1, right? There's not a value less than 1, and there's not a value greater than 26. So do that, and then we call Mystic's unique method, which says any number, and I want all numbers in a set to be unique. So you can say for this value, get all the numbers in the set to be unique, because that was part of it. It was a one-to-one mapping between numbers and letters and variables. And this is basically our constrained space we'll be working over, right? With the penalty that the further away it is from an integer or not have a unique point, the more it's penalized. Which means if it just happens to cheat off this space a little bit, it gets hit with an extra penalty. which drives it back in the right direction. Okay, so, and then we just give that to differential evolution solver, again with constraints as our constraint, and penalty is our penalty function. And the thing goes to town, churns for a while, 3, 2, and then 0. So it solved it, and those are all the values of the points. It took a while, right? Look at the function evaluations. But it used differential evolution to solve a integer programming problem. So you can do quite a lot with this stuff. Basically, here's a nasty system of constraints in a moderately medium dimensional space, basically 7 dimensions. Convert that, again, the same song and dance, to conditions, to a penalty. Here, we're going to do a very cheap constraint to integer space by saying I'm going to do a round, right? So I'm rounding everywhere. Therefore, I get integers. This is, again, integer programming. And it goes pretty quick. So I found all unique points. Oh, sorry, they're not all unique points. I don't know, I found the solution of this problem. So you see they start to look a lot alike, where it's do some big nasty mess of constraints, then turn it into a penalty function or a solver, a constraint solver. Sometimes the constraint solvers you have to think about. Penalty functions are very straightforward. So if you'd like to give it a try, I'm not going to make you do it now, but edit the pressure vessel design to do, instead of that, do it where you're adding penalty functions, which means you would have whatever that is, 12, 10 penalty decorators on something. But if you can convert from one to the other, then you have the representation down. Here is here's the pressure vessel design seen below, and it's using symbolic, but if you were to convert to the other type, sorry, it would be 4 decorators. So here's linear and quadratic constraints, just like convex optimization. So we have this system of equations with, we have the one equation subject to that system of equations, those constraints. Essentially what we do is we build all of the dual parameter constraints, all the linear programming constraints into constraints equations, and all the single parameter constraints go into bounds. So I put those into range constraints. These are our penalty constraints. They end up being penalty constraints. And then I will do the same thing. I will wrap the constraints equations into a conditions and into a penalty, and then apply it to the objective function. Okay. So you can try to move between the different variants on those. And basically, this is a fairly short section that I'll finish up with. And this is working with different solver workflows. So one of the things we have is asynchronous and redistributable modes. And if you use here's configuring a solver like we've seen before. Nelder-Mead, set the initial points, set the objective, add a monitor, and then I can step through it. I can say step, 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 step. So I actually control, in an asynchronous way, moving through the algorithm. If I want to do step and analysis, step and analysis, step and analysis, or have two solvers run and exchange state, or build a meta solver around it, it's pretty easy to do that. So you can have solvers basically explore and then talk to each other by exchanging information. You can build all of that stuff in. So then what I do is, at this point, I decide, well, you know what? I'm going to save the solver, and I save it to a pickle file, and it says dumped to the pickle file. I can take that pickle file and I could pass it off, like I said, to n processors and start on n processors, and it would start in the same place it started before. So here is me starting up on another processor, basically just started Python over, loaded solver, loaded the solver from the pickle file, and then did step, and the monitor and everything else picks up where it started from. So it's not saving parameters, it's actually saving the solver, which means you can stick this thing in a database if you like, right? And I actually use I have a package called Klepto. I'll giving a talk on it later in the week. And you can use a database to store arbitrary Python objects as an intermediary between processes on different machines. So if you want to have communication between processes, a cheap way to do it is just pass the objects through a database or a on-file database with Klepto. And that's what you might do here. And this essentially passes the entire optimizer, and then I get bored of stepping through it, so I just say solve, and it'll go through and solve the rest of it down to the termination condition, down there, and then dump it at the end, because I assume since I saved it once, I want to save it again. What you can actually do at that point, if you like, is it's not dead. It's a solver in the state where if I was to type step or solve again, it would spit back at me, yeah, I've already met the termination conditions. So one of the things you can then do is change the termination condition, and you'll restart the solver, okay? So it's another nice way of, if you have a complex surface you want to navigate down, what happens before? You don't find the minima. You're in a local minima. You get an answer, and you know you're close, but you're not at the minima, or you think you're close. What you'd like to do is solve and then explore, right? So you can solve, tweak the solver a little bit and explore. You can do things like say, well, I'll slightly change a termination condition to another type of termination. So instead of stopping after n generations with a gradient difference less than a particular value, then you want to solve after n generations with a normalized gradient after a particular value. And the solver will restart essentially with new stop instructions.
Is there a way to easily actually initialize a completely different kind of solver with the main state of the previous solver?
No. There is a way that I do it, but it's still very ugly right now. So the reduce method, the reduce method, which is used by Pickle, extracts the bits. They're fairly uniform, and that's exactly what I do. I call the reduce method and then just build a solver from those bits with a template where I have the solver being passed in. I don't have a function that does that though, right? So I have a block of code that does it. It could be turned into a function. It should be turned into a function. It's one of those that's on my to-do list. Yeah, they all are on the to-do list. Okay, so there's you saw restarts. You can build in solver save frequency, so it gives you a save to whatever file you are going to be saving to at every 10 steps. This could be a database, right? You could say dump to the database after every 10 steps. It could be a file system directory where it basically dumps to a different file within the directory. And then after you're done, I can load the solver up, and I have a new solver instance, which is basically at the place it was before. Okay, so I won't cover the database integration. You can see that if you come to the talk on whatever it is, Thursday, that I still have to write. Let's look at extension to parallel computing. One of the things that Mystic gives you is a very easy way to go to parallel computing. And just like with the asynchronous solver, where you can start to build your own solvers, you can do the same thing with what I call ensemble solvers in parallel computing. So here is because the solver is pickleable, you can then start to build even weird things like a query like this, helper of the solver in a model where it's going to actually run the solver, where it just takes the model and the solver together, and it builds this kind of objective function which runs the solver. But this objective function is actually going to be a payload for a map function, which is used a lot in parallel computing. So what I'm doing here is I get a pool, which is a worker pool, and then I use IMAP unordered, pool IMAP unordered, and then say IMAP of this helper of solver and model. So this returns to me a function where it's taking 10 random tries over 10 random shots at initial conditions that I'm going to run this solver at. And basically, I've built now a simple way to take fmin_pal, which is one of the dumbest, straightforward, fast algorithms, and make it run n copies of it with random starting conditions distributed across space. So then this runs and does a dumb solve, and you can see out of the whatever I had 10, 20, it solves it twice. It gets close a few times, but it actually solves it twice. And if you were then to evaluate which was the best fit by the cost, you'd have the solution. So you then can do a cheap, fast global minimization using fast algorithms and parallel computing, right? And basically just if you want to get back to global minima, you look for the best cost value. And if you want to do a full surface mapping, then you should actually not only keep these values, but you should actually keep the values in the evaluation monitor as well. All right. So here's the lattice solver that I've built that basically grids up space and then dumps the, well, you can configure which points the solver wants to run on in the lattice, and then it can either be constrained to run in that space or just run in that space. And so I'm basically distributing it evenly over space using the PAL directional solver to be a gradient search down the slope. And I'm going to be working with either parallel Python or serial Python if it's not available. So this is Pathos, and it gives you the same API for parallel and serial computing of different flavors. And then essentially we do the verbose logging monitor, which means it's going to print to the screen, but it's going to print to the screen coming from all the different solvers running at the same time, and then do a plot, blah, blah, blah. The important part is here. Any of the functions that can be run in parallel, any of the solvers that can be run in parallel, like differential evolution. Differential evolution has a population. If we wanted to run the objective function where each of the objective function calls within the differential evolution was run in parallel, you could say set mapper to some map coming from a pool, and that would give you the ability to run those, spawn those function evaluations in parallel. For the lattice solver takes a nested solver, so that means at each one of the lattice points, we're going to drop an optimization algorithm, and the mapper there distributes the optimizers over space and lets them run. And so we're now running with multi-processing on optimizers over space. Matter of fact, if I wanted to, I can further nest inside of that if I had another problem that was large enough to do that, right? That solver that I'm passing in could be a differential evolution solver where I have the mapper there to set to run over the threads if I'd wanted to. So I can work in multi-threaded and multi-processing space just by setting the mapper for each of the optimizers as appropriate. Okay, and then of course you can build map constructs on top of this as well. If you have to do something like a Monte Carlo, where you have a Monte Carlo optimization, or you have one of these uncertainty quantifications or a Bayesian inference problem. And then it basically writes our log file at the end. Okay, so if I run this thing, let me see, I'll just run this guy. There you go. So it's a whole bunch of them running. You can see the different IDs, right? You can see the different IDs for the worker pool. It logs the different IDs, so you can keep track of which was run, and the log matches up, and actually the log reader will read the different IDs, so you can trace down each of those different guys, and this is basically a very dumb algorithm, nearly solving there's the 8th order Chebyshev polynomial, which is pretty hard to do with a steepest descent algorithm, but it does okay. How do I stop this thing? Like that, probably. Oh, that should be good. Not really meant to be run in IPython. All right, so I didn't cover dimensional reduction, which is also available. There's termination conditions that say if this one parameter is tracking another parameter, then they're the same, right? If you start to have a matching path, then remove dimensionality by saying this, they're the same. Or if you're doing something that's a probabilistic optimization and something has a weight of 0, and after a certain number of generations still has a weight of 0, remove the dimensionality there, right? So those are different termination conditions that you can also use. And that basically, what it does is the dimensions reduce, the optimization speeds up because it's lower dimensional. You can basically auto-discover lower dimensional space. So I talked a little bit about those. Global search, I'm just going to run since we're out of time. But what it does is it does two nested parallelism and does a logging monitor, which writes to a file. But I have the file go through klepto, which basically will cache the values. So klepto is a dictionary interface to a database or file system, and it also has a caching decorator. So you can decorate a function that automatically saves the input and output values essentially as the dictionary key and value pair. And what this is going to do is it's going to run the optimizer and keep running the optimizer n number of times until it doesn't find any new minima. Okay, the goal there is that. And so here, you can see what it ran the first time, and Klepto tells me that I had 14 misses. So misses are actually new values. I found 14 minima the first time, and then 6, and then 0, and then 1, 1, 1, 0, 1, 1, 1. And I set it to die when I had 2 iterations with no new minima found. I found 17 total minima. Some of these were duplicates. I found 17 total minima. And the plot, if I remembered to get rid of the log function, the log plot should, let's see. Yeah, that's what I thought. Okay, so let me just do it again and delete the log. Okay, that one found them faster. There is my different convergences of the parameters. I don't have to plot them all at the same time, but so it's written this log file, and then what I can do is use the model plotter, which I think is going to show me that, you know, it's all the blue points are the minima, and all the trajectories going into the minima. There is not one of these that's missed, so it's found all the minima. If I just flip the sign, I can go find all the maxima. I can pick the termination conditions to be something else. Instead of minima or maxima, I could shoot for minima of a derivative or maxima of the derivative, right? And essentially target different elements on a surface. Not only do we have the endpoints for these, you have every point on the trajectory if you'd like, if you save it, basically. So it's a very fast way of doing accurate surface interpolation on an unknown function. Yes. It's everyone. It only stopped when a new minimum wasn't found after two cycles, basically. All right, so all of that is standard trunk stuff. Mystic is due for a new release. It's well documented in the code and poorly documented in tutorials, right? So if you look at the code, you look at the examples, they're all well documented. But things like this tutorial, there's hardly any of. So I'll clean this tutorial up and I'll put it up as reference documentation. And please, if you're interested in Mystic or anything you've seen, contact me about it, especially if there's a particular something in your research that you'd like to use in it that you don't find or that you use a lot as a constraint function or a penalty or something like that. I'd be happy to add it to the package. All right, thank you.